Fine. So very good day to everybody present here and a warm welcome to all my dear students. So this is technological innovation and new media, and in today's class we'll discuss about the architecture of internet multimedia communication. Okay, so where it involves internet structures, and then in second part of today's class we'll discuss about the protocol stack H323 standard. Okay, so this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again, I should thank God for giving me this golden opportunity to deliver this useful session, to share my knowledge among my fellow national, international participants, students, and young researchers. So in today's session, we'll have a short introduction to Internet Multimedia Communication, and then we discuss about PPE, Parallel Protocol Engine. Then we discuss about the architecture of PPE, the separation of isochronous as well as asynchronous traffic, and then we discuss about pipelining in the hardware. We discuss about the concept of this architectural diagram. Then we discuss about PF, protocol filter. Then CAM, content addressable memory, about the history of the protocol stack H323 standard, and about the various components, about the different types of protocols. With the protocols I will be completing today's session. Okay, so I have independent work for you. I will post them in the Google Classroom. Please submit them. As I told you earlier, you will have 5 independent works and then 1 open-ended project work. Okay, so at regular intervals I will be giving you some short videos to discuss the knowledge in our topics. So this is a broad introduction to internet multimedia communication. So normally when you talk about networks, you should definitely talk about FDDI, which is nothing but fiber distributed data interface. So FDDI, ATM, and FCS, frame check sequence, definitely all these are important parameters, and they are going to provide bandwidth roughly around 100 Mbps to 1 Gbps. Okay, for a single workstation it is going to provide that much data rate with regards to the bandwidth. So maybe you take in the case of text, maybe audio, video, animated images, everything, the communication comes up with the high definition standard, high resolution. Okay, definitely with the case of animation, even the quality is not disturbed. Earlier when you take in the case of 2G, even in the case of 3G also, we are not getting that quality whenever you come up with the moving pictures. But now everybody is looking for quality, and whenever you are going for communication, not everybody goes for the concept in the video. They look for much more about the clarity. So when it is not clear, it is not a 4K video, it's not a 8K communication, which means they are just skipping up the part. So we are living in a age where we have surplus amount of data. We have information, what you call data, or maybe information burst out in all of the standards. So for this cooperative teleworking with the video communication, we can also deal with X-ray images as well. And even with the case of X-ray images, whenever you have to infer some fine qualities, extract some useful information from this one, you have to be more clear. For example, let us take in the case, you have to identify the brain part, you have to identify the tumor part. Okay, so which means that the background color, the foreground color, everything should be clear. If it is not clear, means you will misidentify, you will do the wrong calculations with regards to identification part. So for this, we are having to have a new load on this network. So what you have to be the input output subsystem of the workstation. Okay, so this is what you call to be internet multimedia communication. We have having an IP network where you have the multimedia terminal, which is supporting this SIP protocol. We will having the multimedia gateway as well. Server will be giving us the client server connection as well. Okay, and of course you have the multimedia terminal supporting the standard initiation protocol, and soft PC supporting this SIP protocol. Okay, so here, as I told you, there are 2 types of traffic. One is isochronous as well as asynchronous. If you take in the case of isochronous multimedia traffic, before going into isochronous means like uh, the signals are happening, maybe transmitting and maybe receiving at the same time, simultaneously it is happening. So in the case of traffic, it is the multimedia traffic is happening at the same time. Okay, so isochronous multimedia traffic requires transmission of large amount of data, maybe with less delay, with less noise, with less jitter problem as well, but definitely it can tolerate the packet loss rates as well. Okay, so here the delay jitter of more than 10 millisecond, up to less than 10 millisecond, okay, no problem. More than 10 millisecond, it is considered as a problem, or maybe it is considered as disturbing. So here asynchronous traffic in opposite to the isochronous multimedia traffic. Okay, here the file transfer or maybe remote procedure call would be requiring less throughput. Okay, but tolerates no errors. Like isochronous, it will tolerate error up to like 10 milliseconds, it will tolerate. After 10 milliseconds only problem. But here asynchronous traffic, traffic, it will not tolerate any error. Okay, so that is the difference. So here we will have the conventional protocol processing as well. So as I told you, X-ray images, you have to be very clear. You have to be processed much more clarity as well. Okay. So X-ray images must be displayed error free. Okay. The video connection between the doctors, between them, okay, no problem. Even delay also no problem. They can identify. But X-ray images has to be very, very clear. So this conventional protocol processing, it's actually limited by this available processing power as well as the input output bottleneck. So bottleneck is nothing but the entry point through which the signals can transmit and receive. Okay. So for this, we would be using some kinds of multiprocessors, what you call it to be PPE, protocol engine. Okay, and similar architectures as well for the offload protocol processing. So for this, whenever you are using PPE, protocol engine, definitely for the transport protocol stacks, for a network speed of around 150 Mbps, it is found to be very good. So that is the reason we try to use this PPE. But we cannot compromise, we cannot fully guarantee the quality of service, QoS services. That is the major thing with the case of the high speed networks. So PPE, you are going to have a function of the parallel protocol implementation. So the protocol processing, the extra overload that it is going to consume, that it is going to take it out from this entire channel. So PPE, parallel protocol engine, would be having two separate memories. One memory for transmitting and another memory for receiving. So there are two or more processors as well. We have transputers. We have like in the form of T425 transputers. They are connected to the shared memories, one for transmitting, one for receiving. So these shared memories are mapped into the address space, and here we will try to implement this ISO 8802.2 LLC, logical link control layer, as well as this transmission control protocol, internet protocol standard as well. Okay. So with this, you can assure a network bandwidth of 120 Mbps. So next comes full duplex communication. Full duplex almost the same. You can transmit and you can both transmission and reception can take place at the same time. Okay. So whenever you are implementing this PPE, of course, we are dealing with this delay problem. We are dealing with the overhead problem as well. Like the execution time, it is taking more execution time, more bandwidth it is consuming. Delay problem is also there. Okay. So for this, the parallelism is actually implemented for the case of full duplex communication. So maybe if you try to implement a parallel structure, which means you can cope up the problem of this delay as well as overhead as well. So for this, we are going to pipeline the execution between the protocol layers, TCP as well as IP. But whenever you are going to pipeline, it is found to be unsuccessful because everything like for the case of TCP or maybe IP, it is having different pipelining, maybe processing requirements as well. So for this, we are going to have a two processor solution. one processor for receiving and one processor for transmitting. Okay, so definitely that would actually individually speed up the this entire speed. Okay, like 1.7 times it is going to speed up for one particular processor that we are implementing. So we are going to discuss the architecture. So generally the architecture will be having a separate processor for the receiver as well as transmit data memory. So definitely it will try to reduce the memory contention, memory competition. Like everybody will be accessing the memory, that it will be reducing. Maybe at the same time the memory contention is also reduced. Also it can simultaneously transmit and receive at the same time. Also network speed is also not compromised. Okay. So as I told you, transputer links like a T425 standard. So that is established between the sender and receiver. Definitely, but transputer links will have little impact on the performance of the entire system. So PPE, that protocol processing engine performance, it is limited by some operations, what you call to be copying, like from one memory to another memory, like primary to secondary for copying, that it will be limited. Okay, so that is the only drawback, but definitely it can go for the transmission control protocol checksum calculation, that it is okay. Even when the software was switched off also, it can do the calculation. Right. So the protocol processing performance, generally it will be in the range of 100 Mbps for the throughput of the rate of 27 Mbps. Okay. So the processing power is also one disadvantage. Like the available processing power is also very less. So that would be the factor that generally it would be having an extra workload or maybe overload on the interface hardware as well. Okay. Still the performance is not sufficient for high speed networks. So high speed networks, it is still not functioning well, and the processor memory cannot be scaled to the high speeds. That's what I'm telling you. High speed networks, this interface hardware is not actually suitable. So this is actually separation of the isochronous as well as asynchronous traffic. So QoS is one such factor that has to be of major concern whenever you are dealing with this isochronous as well as asynchronous. So there has to be separate paths for the processing of two traffic types. So you have to have individual sufficient resources as well to handle isochronous. Asynchronous, okay, it cannot handle any error, but isochronous has to handle or maybe tolerate some error. So which means you have to provide sufficient resources to handle the isochronous traffic. So protocol processing as well as workstation interfaces are separated, and we are going to have a dedicated workstation interface for the speeding purposes for the high speed networks. As I told you, parallelism is very much important. So our TCP as well as IP implementation for this parallel protocol engine should be having a parallelism concept between the sender and the receiver. So that if you try to implement, then you can improve the speed as well. And here the communication between the sender and receiver can be accommodated with a low speed serial message links. So that is how it is going to have a serial message link between the sender and the receiver. So here you are going to split the memory into the sender and receiver part. So this actually reduces the memory competition or maybe memory contention, and definitely the memory devices would be less accessible. So that would create a less overhead, and of course you can transmit and receive at the same time and at the same speed for the high speed networks. So as I told you, copying is one such disadvantage. Like copying is one advantage and disadvantage. So maybe for the copying or maybe the computing the checksum value as well. So that degrades the performance. So these operations you can come up with a closely coupled pipeline of hardware devices that is going to overlap the header processing. So here the communication adapter, it is going to split up into send slides as well as receiver sides, and for this you are going to have a hardware coupled device. So hardware pipeline and separate processing units as well, host interfaces as well, you are going to have for the isochronous as well as asynchronous traffic. So here we will have the network access unit. We will be having MAC medium access control, and you are going to have for the frame service, you are going to have a frame oriented interface for the pipeline services. So this is the architecture of the PPE. So here you will have the interfaces. You will have asynchronous processing for asynchronous traffic, isynchronous processing for asynchronous traffic. Okay, and you'll be having copy DMA, checksumming CRC, network access as well. Okay, so this is the transmit pipeline, and for the receive pipeline, network access, protocol filter, PVF, checksumming, cyclic redundancy check, and then copy DMA. So PF is actually the device which is going to perform this demultiplexing operation, and we have a connection number for which the protocol headers, and you are going to extract the information from the connection, and you are going to have the CRC, okay, cyclic redundancy check unit, or maybe checksum unit, which is going to use this connection number for calculating the check sequence, okay, CS, okay. So we'll, as I explained in the diagram, we have this DMA, direct memory access unit as well. So that would be using this connection number for forwarding the isochronous as well as asynchronous data to the required units. As you can see from the copy DMA, it is going to go with the cyclic redundancy check. It is going to forward to the remaining units. So every unit, if you can see, every unit that we discussed will be having a dedicated interface as well, and every processing unit will be getting the data from the workstation interface, and it will be forwarding the required asynchronous as well as asynchronous data to the transmit pipeline. So this connection number, it will be determining whether this check sequence algorithm, whether it can be used and where it can be calculated, the check sequence where it can be calculated. Then you have the PF protocol filter. So that is the central part. This is very important for handling this isochronous as well as asynchronous traffic. So every incoming packet header, it will be scanning, okay, and then it will be extracting the information, because only when you extract the information we can form a definite connection, okay, through the connection number. So if the connection is found, which means that the protocol type as well as the connection number are returned. The connection number, as I told you, it's a unique number for the connection control information. So this is the protocol address tree structure. Protocol type, you have the PV, protocol version. So path A, path B, protocol version, and from this you have source address C, B, D, then destination A, D, E, okay, and from this source destination port P, Q, and R, okay. So that is how it goes. So you can go with either paths, but they are interconnected, and of course from the destination address it will go only to the source destination port, okay. This from here, this from here. Destination address E from the path B will be interconnecting with the source destination port Q as well as R. Right. Here you have CAM, content addressable memory. So connection, it will be defined by the path. So from the path only comes this content addressable memory. CAM row will be having this information about the entire tree structure, the protocol type that it is using, also the information about this address, okay. So for each branch of the tree, CAM would be returning the address of the matched word. So what it is matched, then it will be returned. So you'll have this PF will be having this two hardware state machines will be built across this content addressable memory. Then you have CNB, connection number builder. So you'll be having this connection number builder will be having the address which is generated from this CAM, content addressable memory, and it will be building a very peculiar connection number. So as the connection detection works in the order of one time, then the protocol filter will be running at the higher network speed. And of course you will have mask generator as well, that will be extracting the relevant header fields from the protocol header, and the mask is being generated and it is compared with the CAM. Now if it is compared, okay, when the match for a word is has to be found, then connection number builder will be building a unique connection number. So this is the protocol filter. Mask generator we already talked about. From the input data, mask generator has been it is going into mask generator. From this, the mask has been generated and it has been compared with the CAN. So when it is compared, it is equal means the match is found, and from that connection number builder will be producing a unique connection number. Right. So we move on to the second part of today's class, which is protocol Stack-H.323 standard. So that is actually coming under ITU, International Telecommunication Union. Okay, so ITU, International Telecommunication Union standardization sector. Okay, so that we will be having this AV communication, audio visual communication sessions. So H323 standard will be having definite standards for equipments, for computers, for devices, for services as well, in order to support real-time text, audio, video, visual, as well as data details as well. So with the case of IP-based video conferencing, we will be using this H323 standard. Similarly, for the VoIP, Voice over Internet Protocol, and of course Internet Telephony as well. Normally, if you can see in real time, H323 we will utilize this VoIP, okay, Voice over IP. Right. So H323 standard depends on this IETF, Internet Engineering Task Force, and RTCP, Real Time Control Protocol, and RTP, Real Time Protocol as well, to support this audio visual communications. So when you go for the history, so normally it came up in October 1996. So it was part of the H328 standard. After that only 323 developed. So as I told you, it is coming under ITU standardization sector. So with the earlier it had only limited features only, but now it is establishing calls, it is sharing the compressed audio video techniques. Also it is having the start as well as the endpoints given. So in H323 we are having four type of component. One is terminal, gateway, gatekeeper, and then MCU, multi-point control unit. Okay. So we'll go to the terminal. So it is nothing but the client endpoint. So we are having bidirectional real-time multimedia communication. So for the H323 terminal, generally it can be a computer or be a system or be device that is going to run this H323 stack. Of course, the multimedia applications as well. And then we have gateways. As the name implies, gateway, it is the entry or maybe exit point. So it is going to connect two distant networks as well, and this gateway is going to provide connectivity between H323 network as well as non H323 network as well. So it can go for the call setup as well as release, transforming the media formats, conversion procedures, everything can take place, and switching operations can also be performed by this gateway. And then you will have gatekeepers. So that is considered as the central or maybe the core point for every call. So every call is being monitored and registered with the H323 endpoints. So they will be having some control services as well. And if these services are available, then of course endpoints can use these services. And then you have MCU, multi-point control unit. So it is going to support for conferencing, like maybe 3 or more H323 endpoints or maybe terminals as well. And whoever participates in the conference can use this multi-point control unit connection. So this is the architecture model of H323. We have the gatekeeper, the internet is at the center. Here we have the gateway, and we have the telephone, IP telephone, okay, telephone network. So it is connected to different telephones. See, these are the protocols of H323. We have the speech layer, control layer, G7XX, RTCP, H225, and then Q931, 4.25. That's actually for the call control and call signaling, and then user datagram protocol, TCP, transmission control protocol, IP, internet protocol as well. So we are going to explain about these protocols. Okay, for the G711 or G723.1, definitely for the compression you can use it, and H245 So it is going to allow these terminals to negotiate which protocol can actually use for compression, which protocol should not be used. So that negotiation procedure H245 is using. So you can also, another function would be for the negotiating for the bit rate as well. And then RTCP, a real transport control protocol for the controlling the real-time protocol channels as well. And Q931 for the establishing and then releasing connections, dial tone, and then making the ringing sound, everything Q931 is providing. And then H225 we will be having this PC2 gatekeeper channel, what you call it to be the remote access server channel. It will be allowing the terminals to join as well as leave the zone, request as well as return the available bandwidth, and of course to provide the status updates. Finally, RTP, real-time protocol for the actual data transmission. So this is the independent work. We are going to work on the elements of visual perception. So that actually comes under image processing, and then steps in image processing systems, digital image system, image acquisition, sampling, and quantization. So this you are going to complete them, submit them in your Google Classroom. Once again, I am reminding you 5 independent works and 1 open-ended project.